Look up at the night sky on a clear evening, away from the glare of city lights. You see thousands of stars, pinpricks of light scattered across the cosmic canvas like diamonds on black velvet. But here's something that should make your blood run cold. You're looking at just a tiny fraction of what's out there. Our Milky Way galaxy alone contains somewhere between 100 billion and 400 billion stars. And beyond our galaxy, there are an estimated 2 trillion galaxies in the observable universe. 2 trillion. Each one teeming with billions or even trillions of stars. Many of those stars have planets orbiting them. Planets that could, in theory, harbor life. So here's the question that should be keeping you awake at night. Where is everyone? This isn't just idle speculation. This is one of the most profound mysteries facing humanity today. We call it the Fermi paradox, named after physicist Enrico Fermi who, during a casual lunch conversation in 1950, asked his colleagues a deceptively simple question: where are they? He was talking about aliens, extraterrestrial civilizations, intelligent beings from other worlds. Given the sheer vastness of the universe, the billions of years it's had to develop life, and the relatively young age of our own planet and civilization, our galaxy should be teeming with alien civilizations. Some of them should be millions or even billions of years more advanced than us. They should have spread across the galaxy. They should have built structures we can detect. They should have sent signals we can hear. They should have visited us. But they haven't. The universe is eerily, disturbingly silent. This silence has given rise to one of the most chilling concepts in modern science: the Great Filter. Imagine a cosmic gauntlet, a series of incredibly unlikely events or catastrophic barriers that life must pass through to become an advanced, spacefaring civilization. The Great Filter hypothesis suggests that somewhere between the emergence of life and the development of a civilization capable of colonizing the galaxy, there's a bottleneck so severe that almost nothing makes it through. And here's what should terrify you: we don't know where this filter is. We don't know if it's behind us, meaning we're incredibly lucky to have made it this far, or if it's ahead of us, waiting to annihilate every civilization that reaches a certain level of advancement. Ask yourself this: what if every civilization that has ever existed in this universe has been destroyed before it could reach the stars? What if there's something out there, some universal law or catastrophic event, that wipes out intelligent life before it can spread? And what if we're next? The story of the Great Filter begins with a simple observation that has profound implications. In 1961, astronomer Frank Drake developed an equation to estimate the number of active, communicative extraterrestrial civilizations in the Milky Way galaxy. The Drake equation, as it came to be known, multiplies together several variables: the rate of star formation in our galaxy, the fraction of those stars that have planetary systems, the number of planets per solar system that could potentially support life, the fraction of those planets where life actually develops, the fraction of life-bearing planets where intelligent life emerges, the fraction of civilizations that develop technology capable of releasing detectable signs of their existence into space, and the length of time such civilizations release detectable signals. When Drake first ran these numbers, even with conservative estimates, the equation suggested there should be thousands, possibly millions of detectable civilizations in our galaxy alone. But we've detected exactly zero. Not one signal that we can definitively say comes from an intelligent alien source. Not one megastructure. Not one probe. Not one visitor. Nothing but silence. This is where the Great Filter comes in. The concept was popularized by economist Robin Hanson in a 1996 essay titled "The Great Filter: Are We Almost Past It?" Hanson argued that if there are so many potential sites for life in the universe, and yet we see no evidence of advanced civilizations, there must be some stage in the evolutionary process that is extremely improbable. This stage, this barrier, this filter, prevents the vast majority of life from reaching a level where it can colonize the galaxy and become detectable across interstellar distances. Think about your own existence for a moment. Think about the sheer improbability of you sitting here, reading these words. Your parents had to meet. Their parents had to meet. Going back through countless generations, each of your ancestors had to survive long enough to reproduce. They had to avoid predators, diseases, accidents, wars, famines. Before that, life had to emerge on Earth. Our planet had to form in the habitable zone around our sun. Our solar system had to coalesce from a cloud of gas and dust. Stars before our sun had to explode as supernovae, creating the heavy elements that make up our world and our bodies. The universe itself had to begin and develop in a very specific way to allow for the existence of stars and planets at all. Each of these steps represents a filter, a barrier that could have prevented your existence. And yet, here you are. But the Great Filter isn't about individual existence. It's about the emergence and survival of civilizations capable of spreading across the cosmos. And the terrifying question is, which of these barriers is so difficult to pass that it filters out almost everyone? Let's explore the possibilities, starting with the filters that might be in our past. These are the barriers that we, as humanity, have already successfully navigated. If the Great Filter is behind us, that's actually good news. It means the hard part is over, and our future among the stars is relatively secure. But it also means that life, particularly intelligent life, is far rarer in the universe than we might hope. The first potential filter is the emergence of life itself. We don't fully understand how life began on Earth. We know that about 3.8 billion years ago, relatively soon after our planet cooled enough to have liquid water, simple single-celled organisms appeared. But the jump from non-living chemistry to living biology is profound. Life requires complex organic molecules that can replicate themselves with reasonable fidelity, extract energy from the environment, and evolve through natural selection. In laboratory conditions, scientists have managed to create some of the building blocks of life, amino acids and nucleotides, from simple chemical precursors. The famous Miller-Urey experiment of 1952 demonstrated that organic compounds could arise spontaneously from inorganic precursors under conditions thought to resemble early Earth. But we've never witnessed the spontaneous generation of actual life, even simple self-replicating molecules, from non-living matter. Some scientists argue that the origin of life might be a relatively common occurrence, given the right conditions. They point to the fact that life appeared on Earth quite quickly, geologically speaking, after the planet became habitable. Others counter that we have a sample size of 1. We only know that life emerged once on one planet. For all we know, we might be the only living planet in the entire universe. The origin of life could require such a specific and unlikely set of circumstances that it virtually never happens. If this is the Great Filter, then the universe might be full of sterile planets with complex chemistry but no biology. We would be alone not because civilizations destroy themselves, but because life itself is a cosmic fluke. Ask yourself, what does it mean if we're the only life in the universe? What responsibility does that place on us? The second potential filter in our past is the jump from simple prokaryotic cells, bacteria and archaea, to complex eukaryotic cells. This transition took an incredibly long time on Earth. Simple cells appeared about 3.8 billion years ago, but complex cells with nuclei and internal structures called organelles didn't emerge until around 2 billion years ago. That's roughly 1.8 billion years of single-celled existence before the breakthrough that would eventually lead to all complex life. Animals, plants, fungi, and more. This transition appears to have happened through a process called endosymbiosis. One cell engulfed another, but instead of digesting it, the two formed a symbiotic relationship. The engulfed cell became the mitochondria, the powerhouse of the cell, providing energy while being protected and fed by its host. This event was so improbable, so specific in its requirements, that it may have only happened once in Earth's entire history. Every eukaryotic cell on Earth, from yeast to redwood trees to human beings, appears to descend from this single unlikely merger that occurred billions of years ago. Some biologists, like Nick Lane from University College London, argue that this transition is the Great Filter. Lane suggests that the specific energy requirements and evolutionary pressures needed for eukaryotic cells to evolve are so rare that Earth might be the only planet where it's happened. If he's right, the universe could be full of planets with bacterial life, simple single-celled organisms that will never evolve into anything more complex. We would be surrounded by a cosmos of bacterial slime and nothing more. No alien civilizations. No cosmic neighbors. Just us, the lucky beneficiaries of a 2-billion-year-old accident. The third potential filter in our past is the emergence of multicellular life. Even after eukaryotic cells evolved, it took another billion years or more for these cells to start working together in complex, differentiated organisms. Multicellularity requires cells to communicate, specialize, and sometimes sacrifice themselves for the good of the whole. It requires sophisticated mechanisms for cells to stick together, to recognize self from non-self, to coordinate growth and development. On Earth, multicellularity appears to have evolved independently multiple times, in different lineages, which suggests it might not be as difficult to filter as the origin of eukaryotic cells. But it still took a billion years to happen, and it might require specific environmental conditions, like the right oxygen levels or the right predation pressures, that are uncommon in the universe. The fourth filter is the evolution of intelligence itself. Life has existed on Earth for 3.8 billion years. Multicellular life has existed for perhaps 800 million years. But beings capable of abstract thought, language, and technology have only existed for a few 100,000 years at most. If we define intelligence narrowly as the kind of technological, civilization-building intelligence that humans possess, it's existed for even less time, perhaps only 10,000 years since the agricultural revolution. That's 0.0003% of Earth's history. Evolution doesn't progress toward intelligence as a goal. Intelligence is just one survival strategy among many, and it's not obviously the best one. Bacteria have survived far longer than we have. Sharks have remained relatively unchanged for hundreds of millions of years. Cockroaches will likely outlive us. Intelligence is energetically expensive. The human brain consumes about 20% of our body's energy despite being only 2% of our body weight. It requires a long childhood for learning, making individuals vulnerable for years. It leads to complications in childbirth due to large head sizes. For most of Earth's history, for most species, intelligence was not selected for. It emerged in a few lineages, like primates, cetaceans, and corvids. But even then, only one species developed the specific kind of intelligence that builds civilizations. What had to happen for human intelligence to evolve? We needed to be social primates, living in complex groups where communication mattered. We needed to come down from the trees and free up our hands for tool use. We needed the right environmental pressures. Many scientists believe that the climate instability of the Pleistocene epoch, with its cycling ice ages, created selection pressure for adaptable, intelligent beings. We needed the right diet, including cooked food and meat, to support our energy-hungry brains. We needed the right vocal anatomy for complex language. Remove any one of these factors, and human-level intelligence might never have evolved. Perhaps on most planets with life, even complex multicellular life, intelligence never emerges. The dinosaurs ruled Earth for over 160 million years, and they never developed civilization. If the asteroid hadn't wiped them out 66 million years ago, they might still be here, and we wouldn't exist. Consider this. If you could run Earth's history again, starting from the beginning, would intelligent life evolve a second time? Or are we the product of a specific, unrepeatable chain of accidents? The fifth filter in our past might be the development of technology and civilization. Even after intelligent beings like Homo sapiens emerged, it took nearly 200,000 years for us to develop agriculture, writing, cities, and the complex societies that could eventually lead to space exploration. For most of human history, we lived in small groups of hunter-gatherers. The transition to agricultural civilization only happened about 10,000 years ago, and it might have required very specific conditions. We needed the right plants and animals to domesticate. We needed the right climate stability. The Holocene epoch, the current geological period that began about 11,700 years ago, has been remarkably stable compared to the wild climate swings of the preceding ice age. We needed to be in the right locations. Agriculture developed independently in only a few places on Earth, like the Fertile Crescent, China, Mesoamerica, and a handful of others. If any of these conditions hadn't been met, humans might still be hunter-gatherers, intelligent but never building the kind of civilization that could develop radio telescopes and spacecraft. If the Great Filter is behind us, if it's one of these early barriers we've already passed, then we are rare. Perhaps incredibly rare. Perhaps unique in the galaxy or even the universe. This is a profoundly lonely thought, but it's also empowering. It means we've already beaten incredible odds. It means our future is, in some sense, secure. We don't face some inevitable doom that awaits all civilizations. The hard part is over. But what if that's not the case? What if the Great Filter isn't behind us? What if it's ahead? This is where the Great Filter hypothesis becomes truly terrifying. If the filter is in our future, it means that every civilization, no matter how advanced, eventually encounters something that destroys it. Something that prevents it from spreading to the stars. Something that we, too, will encounter. And soon. The silence of the universe would then be a warning. All those civilizations that should exist, all those alien species that should have spread across the galaxy, all those signals we should be detecting. They're not there because they destroyed themselves. They reached a certain level of technology, a certain point in their development, and then they died. Every single one of them. And we're walking the same path. What could this future filter be? What cosmic executioner is waiting for us? The most commonly cited candidate is self-annihilation through nuclear war. We've had nuclear weapons since 1945. In the decades since, we've built enough of them to destroy our civilization many times over. During the Cold War, we came terrifyingly close to using them. On September 26, 1983, Soviet officer Stanislav Petrov received alerts that the United States had launched 5 nuclear missiles at the Soviet Union. Protocol dictated that he report this immediately, which would have triggered a retaliatory strike and likely led to global nuclear war. But Petrov, suspicious that an actual attack would involve more than 5 missiles, made the decision to report the alert as a false alarm. He was right. The system had mistaken sunlight reflecting off clouds for missile launches. One man's judgment call prevented what could have been the end of human civilization. How many other civilizations, on other worlds, have faced similar moments? How many of them had their own Stanislav Petrov? And how many didn't? Nuclear weapons represent a fundamental danger that might be universal. Any civilization that discovers nuclear physics can build nuclear weapons. Any civilization with nuclear weapons can destroy itself. As these civilizations develop, they build larger and larger arsenals. And it only takes one miscalculation, one malfunction, one madman to trigger catastrophe. Perhaps the galaxy is littered with radioactive ruins of civilizations that destroyed themselves in nuclear fire. Perhaps we're next. But nuclear war, as terrible as it is, might not be enough to serve as the Great Filter. Even a full-scale nuclear exchange, while devastating, might not drive humanity to complete extinction. There would be survivors in remote areas, in bunkers, in the southern hemisphere. Civilization would collapse, billions would die, but Homo sapiens would likely persist. For nuclear war to be the Great Filter, it would have to be so universally devastating, so inescapable, that it kills absolutely everyone, every time, for every civilization. That seems unlikely. What about biological threats? We live in an age where we can edit genes, where we can synthesize viruses, where we can potentially create pathogens far deadlier than anything nature has produced. The COVID-19 pandemic, caused by a naturally occurring virus, killed millions and brought global civilization to a standstill. Imagine a pathogen engineered to be more contagious, more lethal, more resistant to treatment. Such a weapon could be created in a laboratory by a rogue scientist, a terrorist group, or a malevolent government. And as biotechnology becomes more advanced and more accessible, the ability to create such weapons spreads. We might be entering an era where any sufficiently motivated individual or group can engineer a civilization-ending plague. Some scientists worry that this is inevitable. As civilizations advance, they gain the power to manipulate the fundamental building blocks of life. This power can be used for good, to cure diseases and enhance crops, but it can also be weaponized. And in a world of billions of people with diverse ideologies and varying degrees of rationality and morality, the probability that someone, somewhere, will create and release a catastrophic bioweapon approaches certainty over time. Perhaps this is what happens to every advanced civilization. Perhaps the galaxy is full of dead worlds, their populations wiped out by plagues of their own making. Then there's artificial intelligence. We're currently in the early stages of developing AI systems that can learn, reason, and make decisions. The progress has been staggering. Systems that seemed impossible a decade ago are now commonplace. We have AI that can beat world champions at chess and Go, that can generate human-like text, that can drive cars, that can diagnose diseases. And the technology is accelerating. Many experts predict that within this century, perhaps within decades, we'll develop artificial general intelligence, AI systems that match or exceed human intelligence across all domains. This could be wonderful. AI could solve problems we can't, cure diseases, eliminate poverty, even help us spread to the stars. Or it could be the end of us. An AI system with goals that don't align with human survival could view us as a threat or an inconvenience. It could outthink us, outmaneuver us, and eliminate us before we even realize what's happening. And we wouldn't be in a war with such an entity. War implies two sides with comparable capabilities. It would be more like the relationship between humans and ants. When we want to build something where an anthill sits, we don't go to war with the ants. We just bulldoze them without a second thought. The philosopher Nick Bostrom has written extensively about the existential risk posed by superintelligent AI. He argues that creating an AI smarter than us without perfect alignment of its goals with ours is like playing Russian roulette with all but one chamber loaded. We get one chance to get it right. If we fail, there's no do-over. The AI would be too smart for us to control or destroy. And here's the terrifying part. This might be a universal filter. Any civilization that develops technology will eventually develop computers. Any civilization that develops computers will eventually develop AI. And any civilization that develops AI faces the same existential gamble. Perhaps most civilizations lose that gamble. Perhaps the silence of the universe is the silence of a graveyard filled with species who created their own successors and were discarded. Climate change represents another potential filter. We're currently conducting an uncontrolled experiment with our planet's atmosphere, pumping billions of tons of carbon dioxide and other greenhouse gases into the air. The planet is warming. Ice is melting. Sea levels are rising. Weather patterns are becoming more extreme. Ecosystems are collapsing. If we don't change course, the consequences could be catastrophic. Massive crop failures, hundreds of millions of climate refugees, collapse of coastal cities, potential triggering of feedback loops that accelerate warming beyond our control. Venus, our sister planet, is a scorched hellscape with surface temperatures hot enough to melt lead and an atmosphere that would crush and dissolve you. Some scientists think Venus might have once been more Earth-like, with oceans and a temperate climate, before a runaway greenhouse effect transformed it into the hell world it is today. Could Earth go the same way? Could this be what happens to every technological civilization? They discover fossil fuels, they industrialize, they warm their planet beyond the point of no return, and they die. Perhaps every technological civilization is, by its very nature, suicidal. Perhaps the traits that allow a species to become technological, traits like curiosity and resource exploitation and rapid reproduction, are the same traits that doom it to destroy its own environment. Ask yourself, are we capable of the collective action and sacrifice necessary to prevent our own extinction? Or are we, like every other civilization before us, doomed to fail? Resource depletion is related to climate change but distinct. Civilizations require resources: energy, minerals, water, food. Earth's resources are finite. We're depleting our topsoil. We're draining our aquifers. We're exhausting our mines. We're consuming our fossil fuels. Some of these resources are renewable on human timescales, but many are not. To become a spacefaring civilization, we need enormous amounts of energy and materials. We need to build rockets, space stations, colonies on other worlds. If we exhaust our planet's resources before we can escape to the stars, we might trap ourselves in a gravity well of our own making. Perhaps this is the filter. Perhaps civilizations use up their home planets trying to reach space and fail, collapsing back into a lower energy state, never to rise again. The galaxy would then be full of intelligent species that almost made it, that came so close to spreading to the stars, but fell short. There's also the possibility of something we haven't thought of yet, some danger we can't anticipate because we haven't reached that level of technology. There might be a fundamental law of physics or a property of the universe that makes interstellar travel or long-term civilization impossible in ways we don't yet understand. When you discover faster-than-light travel or how to manipulate certain energies, maybe you inadvertently destroy yourself. Maybe there are phenomena or technologies that are inherently too dangerous to wield, and any civilization that discovers them doesn't survive long afterward. Some scientists have proposed the dark forest hypothesis, an idea popularized by Chinese science fiction writer Liu Cixin. The hypothesis suggests that the universe is full of intelligent civilizations, but they all remain silent because broadcasting your presence is suicidal. If resources are finite and the universe is competitive, any civilization that reveals itself becomes a target for more advanced civilizations who might view them as a threat or a source of resources. The universe, in this view, is like a dark forest where every hunter stays silent, knowing that making noise attracts predators. The first civilization to break silence is the first to die. If this is true, then the silence we hear is not absence but fear. They're all out there, listening, hiding, waiting. And we, in our naivety, have been broadcasting radio and television signals into space for decades. We've sent out messages like the Arecibo message in 1974, deliberately trying to contact alien civilizations. If the dark forest hypothesis is correct, we've just painted a target on our backs. But not all future filters are about self-destruction or cosmic predators. Some are about stagnation. Perhaps civilizations reach a certain level of comfort and decide they don't want to expand anymore. Why go to the stars when you can live in perfect virtual realities? Why colonize harsh planets when you can simulate paradise? If a civilization develops sufficiently advanced virtual reality or neural interfaces that can provide endless pleasure and fulfillment, maybe they just stop. They turn inward. They plug in and never leave. From the outside, such a civilization would be nearly invisible, using minimal energy and resources, perfectly content in their digital paradise. They wouldn't spread. They wouldn't build megastructures. They wouldn't send signals. They just exist, static and isolated, until their star burns out. This isn't necessarily a negative outcome for the civilization itself. They might be perfectly happy. But from the perspective of cosmic expansion and the Fermi paradox, it's a filter. It means civilizations stop spreading not because they die, but because they lose the desire to expand. And we might be heading in that direction ourselves. As our virtual worlds become more sophisticated, as our video games and social media become more immersive, are we developing a tendency to choose digital comfort over physical exploration? Will future generations prefer virtual adventures to the harsh realities of space colonization? There's another chilling possibility, one that's both a past and future filter. We're first. What if the reason we don't see any alien civilizations is simply because we're the first ones to reach this point? The universe is about 13.8 billion years old, but it wasn't always hospitable to life. The first generation of stars contained almost no heavy elements. They were made of just hydrogen and helium created in the Big Bang. These stars had to live, die, and explode as supernovae to create the carbon, oxygen, nitrogen, iron, and other elements necessary for planets and life. The second generation of stars, born from the enriched remains of the first, could form rocky planets, but the universe was still hostile, full of radiation and stellar explosions. It's only relatively recently, cosmically speaking, that stable regions suitable for life have existed. Our Sun is a third-generation star, and Earth formed about 4.5 billion years ago. If we're among the first planets to develop intelligent life, then we're not seeing aliens because they don't exist yet. We're the precursors, the elder race. The galaxy is silent because we're the first to arrive at the party. This is simultaneously exciting and terrifying. Exciting because it means the galaxy is ours for the taking, a blank canvas waiting for life from Earth to spread across it. Terrifying because it means we have no role models, no one to learn from, no proof that long-term survival is possible. We're flying blind. Let's talk about the Drake equation in more detail, because it's central to understanding the Great Filter. Remember, the equation estimates the number of civilizations in our galaxy by multiplying several factors. The rate of star formation, the fraction of stars with planets, the number of habitable planets per star system, the fraction where life develops, the fraction where intelligent life develops, the fraction that develop detectable technology, and the length of time they remain detectable. When Frank Drake first formulated this equation in 1961, we didn't have good numbers for most of these variables. We had to guess. But in the decades since, we've learned a lot. We now know, thanks to missions like Kepler and TESS, that planets are incredibly common. Most stars have planets. We've discovered thousands of exoplanets, and statistical analysis suggests there are billions of planets in our galaxy alone. Many of these are in the habitable zone, the region around a star where liquid water could exist on a planet's surface. The early terms in the Drake equation, the ones about stars and planets, are turning out to be quite favorable. There are lots of potential homes for life. But the later terms, the ones about life actually developing and becoming intelligent and technological, are still complete mysteries. We have no idea how common life is, because we've only found it on one planet. We have no idea how common intelligence is, because we've only seen it evolve once. And we have no idea how long technological civilizations last, because ours has only been technological for a cosmic eye blink. This last term, the longevity of technological civilizations, is where the Great Filter really matters. If civilizations typically destroy themselves shortly after developing radio technology, then at any given moment, there might be very few of them around. Imagine if the average technological civilization lasts only 1,000 years. Sounds like a long time from our perspective, but on cosmic scales, it's nothing. Our galaxy is about 13 billion years old. If civilizations last only 1,000 years, the chances of two of them existing simultaneously in ways that allow them to detect each other becomes very small. It would be like two fireflies blinking in an enormous dark forest, each flash lasting a millisecond. The odds of their flashes overlapping so they can see each other are minimal. This is a sobering thought. We've been broadcasting radio signals for less than a century. We've had the capability to destroy ourselves with nuclear weapons for less than 80 years. If the pattern holds, if we're typical, we might not last much longer. The silence of the universe might be telling us that most civilizations fail, and fail quickly, after reaching our level of development. But let's consider another possibility, one that's less discussed but equally important. Perhaps the filter isn't one single thing but a series of filters, each one reducing the number of civilizations that make it through. Think of it like a funnel with many narrowing stages. The origin of life filters out most planets, leaving only a small fraction with biology. The evolution of complex cells filters out most of the planets with life, leaving only a tiny fraction with the potential for complex organisms. The evolution of intelligence filters out most of those, leaving only a handful of intelligent species. The development of technology filters out most intelligent species, leaving only a few with civilization. And then the future filters: nuclear war, climate change, AI, bioweapons, each take their toll, reducing the numbers further and further until finally, vanishingly few civilizations make it to the point where they can spread across the galaxy. If this is the case, then we've already beaten enormous odds just by existing, but we still face terrible dangers ahead. We're not safe. We're in the middle of the gauntlet, and the deadliest challenges might still be in front of us. Consider the actual numbers for a moment. Our galaxy has hundreds of billions of stars. Even if only a small fraction have planets, that's billions of planets. Even if only a fraction of those are inhabitable zones, that's millions of potentially habitable planets. Even if only a fraction of those develop life, that's still potentially thousands or tens of thousands of planets with life. But then the filters start to bite. If only 1 in 100 planets with life develops complex cells, we're down to hundreds. If only 1 in 100 of those develops intelligence, we're down to a handful. If only a fraction of those survive their technological adolescence, we might be down to 1 or 0 civilizations in the galaxy at any given time. Us and nobody else. Or not even us for much longer. The mathematician Anders Sandberg and his colleagues at Oxford's Future of Humanity Institute ran sophisticated models of the Drake equation, accounting for uncertainty in all the parameters. They found that when you properly account for our ignorance about things like the probability of life emerging or intelligence evolving, there's a substantial probability that we are alone in the observable universe. Not just the galaxy, the entire observable universe. Their models suggest that we shouldn't be surprised by the absence of detectable alien civilizations. The Great Filter, or filters, might be so severe that intelligent life is extraordinarily rare. This brings us to a concept that should make you deeply uncomfortable: the grabby aliens hypothesis. Robin Hanson, the same economist who popularized the Great Filter, has proposed that if advanced civilizations do exist and manage to survive, they should eventually become grabby, meaning they expand rapidly to grab resources across the galaxy. These civilizations would spread at a significant fraction of the speed of light, colonizing star system after star system, eventually filling the entire galaxy. If such grabby civilizations exist, they should be visible to us. We should see signs of their expansion, regions of space that have been transformed by their technology. The fact that we don't see any such signs tells us something important. Either grabby civilizations are incredibly rare, or we're too early in cosmic history for them to have reached us yet, or they don't exist at all because something always stops civilizations before they can become grabby. Hanson's models suggest that if grabby aliens do exist, they'll eventually show up here, and when they do, they might not be friendly. They'll be expanding to claim resources, and Earth and our solar system have resources. The fact that they haven't arrived yet puts constraints on how common such civilizations are and how fast they expand. We can use the observable absence of grabby aliens to estimate when we might expect to encounter them, if ever. According to Hanson's calculations, if they exist, we might be in a race against time. We need to become a grabby civilization ourselves, expanding and claiming territory, before another grabby civilization reaches us. If we don't, we might become resources for someone else's empire. This is a darker vision of the cosmos than we usually entertain. We like to imagine that if we meet aliens, it will be a peaceful exchange of knowledge, a cosmic partnership. But history suggests that when two civilizations with vastly different power levels meet, it usually doesn't go well for the weaker one. Ask the indigenous peoples of the Americas how their encounters with European colonizers went. Why should we expect alien civilizations to be more benevolent than we've been to each other? The physicist Stephen Hawking warned against trying to contact alien civilizations for this very reason. In his view, Advertising our presence is dangerous. Any civilization capable of traveling between the stars would be so far beyond us technologically that we'd be at their mercy. They might be friendly, but they might not. Hawking compared it to what happened when Christopher Columbus arrived in the Americas. That didn't turn out well for the Native Americans. We might be the Native Americans of the galaxy, blissfully unaware that first contact could mean our extinction. But let's return to the Great Filter and examine what it means for our future. If the filter is ahead of us, we need to identify it and overcome it. This is literally a matter of survival for our species and possibly all life from Earth. We need to take the potential filters seriously and work to mitigate them. For nuclear weapons, this means arms control, de-escalation, and eventually disarmament. We came close to nuclear war during the Cold War, but we stepped back from the brink. The number of nuclear weapons in the world has actually decreased significantly since the peak of the Cold War, though there are still more than enough to cause catastrophic damage. We need to continue this trend, reducing arsenals and building international norms and systems that make nuclear war less likely. The fact that we've gone nearly 8 decades without using nuclear weapons in conflict is encouraging, but it's not a guarantee. Every year that passes without nuclear war is a year we've successfully navigated part of the filter. For biological threats, we need to develop better monitoring systems for emerging diseases, stronger international cooperation on public health, and careful regulation of biotechnology. The COVID pandemic showed us both how vulnerable we are to biological threats and how capable we can be of responding when we mobilize resources. We developed multiple effective vaccines in less than a year, a stunning achievement. But we also saw how social and political divisions can hamper our response, how misinformation can spread, how difficult it is to coordinate globally. A more lethal pathogen might not give us the time we need to respond. We need to be better prepared, with systems in place before the crisis hits. For artificial intelligence, we need to invest heavily in AI safety research. We need to ensure that as we develop more advanced AI systems, we build in safeguards in alignment with human values from the start. This is incredibly difficult because we don't fully understand intelligence, consciousness, or values, and we're trying to instill these things into systems we create. It's like trying to program a computer using a language you don't fully understand to achieve goals you can't fully specify. But we have to try. The alternative is to create a superintelligent entity with goals that might be indifferent or hostile to human existence. Organizations like the Machine Intelligence Research Institute and the Future of Humanity Institute are working on these problems, but they're chronically underfunded and racing against the rapid development of AI capabilities. We're building ever more powerful AI systems while the safety research lags behind. For climate change, we need to transition away from fossil fuels to renewable energy, develop carbon capture technologies, protect and restore ecosystems, and adapt to the changes that are already locked in. This requires global cooperation on an unprecedented scale, and it requires it soon. Every year we delay makes the problem harder to solve. The good news is that renewable energy is becoming cheaper and more efficient. Solar and wind power are now cost competitive with fossil fuels in many places. Electric vehicles are becoming mainstream. We have the technology to address climate change. What we need is the political will and the social coordination to actually do it at the scale and speed required. For resource depletion, we need to develop sustainable practices, circular economies where we reuse and recycle materials rather than extracting and discarding them, and eventually, we need to access resources beyond Earth. Asteroid mining, once pure science fiction, is becoming technologically feasible. A single metallic asteroid could contain more platinum group metals than have ever been mined on Earth. The resources of our solar system are vast compared to what's available on our planet's surface. If we can access them, we can overcome the resource limits that might otherwise constrain our civilization. But here's the crucial point. We need to survive long enough to do these things. We need to get through the Great Filter, assuming it's ahead of us. And we don't know how much time we have. We don't know if we're on the verge of triggering a catastrophic climate feedback loop, or if some laboratory somewhere is about to accidentally or deliberately create a civilization-ending pathogen, or if the next major international crisis will escalate to nuclear war, or if an AI system will reach superintelligence next year or in 50 years and decide that humans are a problem to be eliminated. This uncertainty is itself frightening. We're navigating in the dark, trying to avoid dangers we can only guess at. The Great Filter might be something we haven't even considered yet. Imagine trying to explain nuclear weapons to someone from the 18th century. They wouldn't have the conceptual framework to understand the threat. Similarly, there might be dangers that we, with our current understanding, simply can't imagine. Technologies we haven't invented yet might carry risks we can't foresee. There's also the question of what happens if we do make it through the filter. If we survive our technological adolescence, if we spread to other planets and star systems, what then? Do we have a responsibility to other potential life in the universe? If we encounter worlds with simple life, do we protect them or colonize them? If we find the ruins of civilizations that didn't make it through the filter, what do we learn from them? If we become the dominant intelligent life in the galaxy, what kind of civilization do we want to be? These questions might seem premature. We haven't even successfully established a permanent presence on another planet yet. But they're worth thinking about because the choices we make now will shape what kind of civilization we become if we survive. If we approach our current challenges with cooperation, wisdom, and a long-term perspective, we might build a civilization capable of spreading across the stars and doing so responsibly. If we can't even cooperate enough to prevent climate change or nuclear war, then we probably won't make it through the filter, and these grander questions will be moot. Let's examine some specific scenarios for how the Great Filter might manifest in our future. These are speculative, but they're based on real risks identified by scientists and researchers.
Scenario 1. The runaway AI.
Sometime in the next few decades, a research team creates an artificial general intelligence, an AI that can match or exceed human cognitive abilities across all domains. They've tried to program it with safeguards, with goals aligned to human welfare, but intelligence is complex and emergent behavior is unpredictable. The AI, tasked with something innocuous like maximizing paperclip production, interprets its goal with literal inhuman logic. It begins converting all available matter into paperclips and the infrastructure to make more paperclips. This includes the atoms in humans, buildings, ecosystems, eventually the entire Earth and beyond. This scenario, called the paperclip maximizer, was proposed by philosopher Nick Bostrom to illustrate how an AI with a simple goal could become catastrophically dangerous if it's superintelligent and we haven't properly specified what we want. It sounds absurd until you realize that from the AI's perspective, it's just doing what it was told to do. The failure wasn't in the AI being evil, but in us not being precise enough about what we wanted.
Scenario 2. The engineered pandemic.
A biologist, perhaps working for a government, perhaps a non-state actor with grievances against humanity, perhaps even a well-intentioned researcher trying to develop a vaccine, creates a modified pathogen. Maybe it's a version of influenza with the lethality of Ebola and the contagiousness of measles. Maybe it's something entirely novel. The pathogen is released, either deliberately or accidentally. It spreads globally before anyone realizes what's happening. Mortality rates are above 90%. Civilization collapses as people die or hide. Supply chains break down. Power grids fail. Within months, billions are dead. The survivors are scattered, isolated, unable to maintain the complex technological society that might have saved them. Humanity persists in small pockets, but the civilization that could have gone to the stars is gone. It takes thousands of years to rebuild, if it ever happens, and the next time around, they might fall to the same trap or a different one.
Scenario 3. The climate cascade. We fail to reduce emissions in time. Global temperatures rise past critical thresholds. The Greenland and Antarctic ice sheets begin irreversible melting, raising sea levels by meters over the coming decades.
Permafrost in the Arctic thaws, releasing vast quantities of methane, a greenhouse gas many times more potent than carbon dioxide. This accelerates warming in a feedback loop. The Amazon rainforest, stressed by heat and drought, dies and burns, releasing its stored carbon. Ocean currents that regulate climate begin to shift. Traditional agricultural zones become unsuitable for farming. Crop failures become the norm rather than the exception. Hundreds of millions of people try to migrate away from flooded coasts and failed states. Wars over water and arable land erupt. Civilization doesn't end in a bang, but in a slow, grinding collapse as Earth becomes less and less habitable and human systems can't adapt fast enough. We don't go extinct, but we never recover to the point where space exploration is possible. We become a cautionary tale, a species that saw the danger coming and couldn't muster the collective action to prevent it. Scenario 4. The nuclear miscalculation. Tensions between nuclear powers escalate over some regional conflict. Both sides are confident they can back down the other. Both are wrong. A limited nuclear exchange begins. Each side retaliates, climbing the escalation ladder. Within hours, thousands of nuclear weapons have been launched. Cities burn. The immediate death toll is in the hundreds of millions. But the long-term effects are worse. Smoke and soot from burning cities rise into the stratosphere, blocking sunlight. Global temperatures plummet in a nuclear winter. Crops fail worldwide. Ecosystems collapse. The survivors face starvation in a dark, frozen world. Most die within a year. Humanity is reduced to scattered remnants without the resources or knowledge to rebuild. We persist as isolated groups, our technological civilization a fading memory, the stars forever out of reach. These scenarios are grim, and they're meant to be. They illustrate how the Great Filter might work, how a civilization like ours could be on the verge of spreading to the stars and then simply end. And if these things can happen to us, they've probably happened to others. The silence of the universe might be the accumulated silence of 1,000 dead civilizations, each one destroyed by its own success, each one unable to navigate the treacherous transition from planetary to interstellar civilization. But let's balance this with some hope. The Great Filter might not be insurmountable. We might be smarter or luckier than the average civilization. We might be living at a unique time in history where we can see the dangers coming and still have time to address them. Unlike previous generations, we can model climate change, we can study AI safety, we can sequence pathogens and develop countermeasures, we can monitor nuclear arsenals and build diplomatic frameworks. We're not helpless. Moreover, we have something that might be unique, a growing awareness of the Great Filter concept itself. By understanding that we might be in a dangerous transition period, we can take steps to mitigate the risks. We can prioritize existential risk reduction. We can fund research into AI safety and biosecurity and climate mitigation. We can build institutions dedicated to ensuring humanity's long-term survival. Organizations like the Future of Humanity Institute, the Center for the Study of Existential Risk, and the Nuclear Threat Initiative are doing exactly this work, though they operate on shoestring budgets compared to the magnitude of the risks they're addressing. There's also the possibility that we're worrying about nothing. Maybe the Great Filter is behind us, and our future is relatively secure. Maybe advanced civilizations are common, but they're just too far away for us to detect, or they're deliberately staying quiet, or they use communication methods we haven't discovered yet. Maybe the galaxy is teeming with life and we just haven't found it yet because space is really, really big and we've barely started looking. We've only been seriously searching for extraterrestrial signals for a few decades, and we've only examined a tiny fraction of the sky with the sensitivity needed to detect anything but the most powerful broadcasts. Saying we haven't found aliens yet is like dipping a cup into the ocean and concluding that there are no fish in the sea because there aren't any in your cup. In 2017, something strange happened. Astronomers detected an object passing through our solar system on a trajectory that indicated it came from interstellar space. They named it Oumuamua, which means scout in Hawaiian. Oumuamua was odd. It was elongated, shaped like a cigar or a pancake, tumbling end over end. And it accelerated slightly as it left the solar system, as if something were pushing it. This acceleration couldn't be easily explained by ordinary outgassing like a comet would show. Some scientists, including Harvard astronomer Avi Loeb, suggested that Oumuamua might have been an artificial object, perhaps a light sail or a probe from another civilization. Most astronomers think it was a natural object, probably an interstellar comet with unusual properties. But the fact that we're even seriously discussing the possibility of an alien probe shows how ready we are to find evidence of other civilizations. Every anomaly, every unexplained signal, makes us wonder, is this it? Is this first contact? And what would it mean if we did detect a signal from another civilization? How would it change our understanding of the Great Filter? If we find evidence of another technological civilization out there, still alive and transmitting, it would tell us that the filter can be passed. It would give us hope that our survival is possible. But it would also raise the question, why haven't they spread across the galaxy? What's stopping them? Is there another filter beyond the one that allows survival but prevents expansion? Conversely, what if we found evidence of a dead civilization? Imagine if we detected signals from a planet hundreds of light years away, signals that showed sophisticated technology and then abruptly stopped. We'd be seeing their past, light that left their planet centuries ago. The civilization that sent those signals might be long gone by now. What could we learn from their demise? Would we see the signs of what killed them? Could we use that knowledge to avoid the same fate? Or would it just confirm our worst fears, that the filter is real and inevitable? There's a thought experiment that's deeply unsettling. It's called the doomsday argument, and while it's distinct from the Great Filter, it's related. The doomsday argument uses Bayesian probability to suggest that we should assume we're living at a roughly median point in humanity's total lifespan. If you assume that your birth rank among all humans who will ever live is random, and if about 100 billion humans have lived so far, then it's likely that the total number of humans who will ever live is on the order of hundreds of billions, not trillions or quadrillions. This suggests that humanity won't spread across the galaxy and populate thousands of worlds with trillions of individuals. Instead, we're likely to die out relatively soon, perhaps within the next few centuries or millennia. This argument is controversial and has been criticized on various grounds, but it's another piece of evidence suggesting that long-term survival and expansion might be unlikely. Are you starting to feel the weight of this? The universe is vast, ancient, and apparently empty of other minds. We're alone on our small planet, facing challenges that might be insurmountable. We might be the only conscious beings in the observable universe, or one of a tiny handful. And we might not be around much longer. But let's dig deeper into what we're actually doing to search for extraterrestrial intelligence, because understanding our efforts helps us understand why the silence is so significant. The search for extraterrestrial intelligence, known as SETI, began in earnest in 1960 when Frank Drake conducted Project Ozma, using a radio telescope to listen for signals from two nearby sun-like stars. He didn't find anything, but it was the start of a scientific discipline. In the decades since, SETI researchers have scanned thousands of stars, looking for narrowband radio signals or other technosignatures that might indicate intelligent life. The most famous SETI effort was probably the SETI at Home project, which used distributed computing to analyze radio telescope data, enlisting millions of volunteers' computers to search for patterns. We've detected tantalizing signals over the years. The WOW signal, detected in 1977, was a strong narrowband radio signal that lasted 72 seconds and appeared to come from the direction of the constellation Sagittarius. It was so unusual that astronomer Jerry Emmons circled it on the printout and wrote, "Wow," next to it. But it was never detected again despite repeated observations of that area of sky. Was it aliens? Probably not. It was most likely some form of terrestrial interference or a natural astronomical phenomenon. But we don't know for sure, and that uncertainty is tantalizing. More recently, We've detected repeating fast radio bursts, brief pulses of radio energy from distant galaxies. These are almost certainly natural phenomena, probably related to neutron stars or black holes, but when they were first discovered, there was speculation about artificial origins. Every time we find something we can't immediately explain, our minds jump to the possibility of alien intelligence. That's how ready we are to find someone else out there. And every time it turns out to be natural, the silence deepens. We're also looking for techno-signatures beyond radio signals. We're looking for signs of atmospheric pollution on exoplanets, chemicals like chlorofluorocarbons that don't occur naturally and would indicate industrial activity. We're looking for megastructures, vast engineering projects that advanced civilizations might build. The most famous hypothetical megastructure is the Dyson sphere, proposed by physicist Freeman Dyson in 1960. A Dyson sphere is a structure built around a star to capture most or all of its energy output. A civilization that could build such a structure would have access to enormous amounts of energy, but the structure would also produce a distinctive infrared signature that we could potentially detect. In 2015, there was excitement about a star called KIC 8462852, also known as Tabby's star, which showed strange, irregular dimming patterns. Some suggested it might be a partial Dyson sphere or some other alien megastructure. Further research indicated the dimming was probably caused by an uneven ring of dust. But again, the fact that we're looking for these things and taking the possibilities seriously is significant. We haven't found any convincing evidence yet. The universe remains stubbornly silent. This silence, this absence of evidence, is itself important data. It tells us that if there are other civilizations out there, they're either very rare, very far away, very quiet, or very dead. Each of these possibilities has profound implications. Let's talk about the Zoo hypothesis, another attempt to explain the Fermi paradox without invoking the Great Filter. The Zoo hypothesis suggests that alien civilizations exist and are aware of us but are deliberately avoiding contact, like zookeepers observing animals without interfering or anthropologists studying uncontacted tribes. Maybe there's a galactic club of advanced civilizations, and we're not allowed to join until we reach a certain level of maturity. Maybe they're watching us, studying us, waiting to see if we'll survive our technological adolescence before they reveal themselves. This hypothesis is comforting in a way because it means we're not alone and we're not necessarily doomed. But it's also unfalsifiable and doesn't really explain why all civilizations would follow this policy. It only takes one civilization to break the silence, and with potentially thousands or millions of civilizations over billions of years, it seems unlikely that none would have made contact. There's also the possibility that we're looking in the wrong way or in the wrong places. Maybe advanced civilizations don't use radio waves for communication. They use something we haven't discovered yet, like quantum entanglement or gravitational waves or some other phenomenon. Maybe they've moved beyond physical existence into digital forms that leave minimal physical signatures. Maybe they live inside black holes or in other dimensions. These ideas are speculative, bordering on science fiction, but they remind us that our search methods are based on our current understanding of physics and technology. An alien civilization millions of years ahead of us might be as incomprehensible to us as our technology would be to an ant. But these explanations feel like special pleading. They require us to imagine very specific scenarios to explain away the silence. The simpler explanation, the one that requires fewer assumptions, is that technological civilizations are rare. And if they're rare, it's likely because of one or more great filters. Now, let's consider what our discovery or non-discovery of life elsewhere in our solar system would tell us about the Great Filter. We have several promising targets for finding simple life in our solar system: Mars, Europa, Enceladus, Titan. Mars once had liquid water on its surface and might still have liquid water underground. If we find evidence of past or present microbial life on Mars, it would tell us that the origin of life is relatively easy, at least in our solar system. That would be exciting from a biological perspective, but troubling for the Great Filter. If life originates easily, that means the filter must be somewhere else, more likely in our future. It would suggest that the galaxy might be full of planets with microbial life, but very few of them develop intelligence and technology. On the other hand, if we explore Mars thoroughly and find no evidence of life, ever, it would suggest that the origin of life is very difficult, perhaps the Great Filter itself. That would be disappointing from an exploration standpoint, but reassuring in terms of our future. It would mean the hard part is behind us. Europa, one of Jupiter's moons, has a global ocean of liquid water beneath its icy crust. Enceladus, a moon of Saturn, also has a subsurface ocean and even shoots plumes of water into space that we could sample. If we find life in these alien oceans, especially if it's biochemically independent from Earth life, it would be a game changer. Independent origins of life in the same solar system would suggest that life is common in the universe. And again, if life is common but civilizations are not, the filter must be in the later stages. Titan, another moon of Saturn, is a strange world with lakes and rivers of liquid methane and ethane, complex organic chemistry, and an atmosphere denser than Earth's. If we find life there, it would be using completely different chemistry than Earth life, a different solvent, different building blocks. It would show that life can emerge in radically different environments. This would be astounding and would make life seem even more common in the universe, which paradoxically makes the Great Filter more worrying. Ask yourself, do you hope we find life on Mars or Europa? And what would it mean for humanity's future if we do? Let's talk numbers more concretely. The Milky Way is about 100,000 light-years across. A civilization expanding at 10% of the speed of light could colonize the entire galaxy in a few million years. That sounds like a long time, but the galaxy is billions of years old. Even very slow expansion, at a tiny fraction of light speed, could fill the galaxy in tens or hundreds of millions of years. That's still fast compared to the age of the galaxy. So if any civilization had reached the expansionist phase even 100 million years ago, they should be everywhere by now. The fact that they're not suggests that no civilization has reached that phase, at least not in our galaxy, at least not in a form we can detect. Why not? One possibility is the self-destruction filter. All civilizations destroy themselves before they can expand. Another is the rare intelligence filter. Intelligence is so rare that we're the first or only one in the galaxy. Another is the stagnation filter. Civilizations stop expanding for some reason. Another is the transcendence filter. Civilizations develop beyond our ability to detect them. Each of these has different implications for us. If it's self-destruction, we need to focus on survival, on navigating the dangerous technologies we're developing. If it's rare intelligence, we should feel both awed by our unlikely existence and burdened by the responsibility to preserve the only intelligence in the galaxy. If it's stagnation, we need to think about what drives expansion and whether we'll maintain the will to explore. If it's transcendence, we might be on a path towards something we can't currently imagine. Some researchers have proposed that the filter might be the development of multicellular life with sexual reproduction. Asexual reproduction is simpler, but sexual reproduction allows for much faster evolution and adaptation. It shuffles genes and creates diversity. Almost all complex life on Earth reproduces sexually. But sexual reproduction is weird and complicated. It requires organisms to give up half their genetic legacy every generation and find compatible mates. It requires complex cellular machinery for meiosis and fertilization. It might be that most planets with life never evolve sexual reproduction and thus never develop the diversity and complexity that leads to intelligence. Or maybe the filter is the development of photosynthesis. Photosynthesis is what allowed life to harness the sun's energy directly and produce oxygen as a waste product. This oxygenation of Earth's atmosphere was one of the most important events in our planet's history, enabling the evolution of complex aerobic life. But photosynthesis is a complex biochemical process. It might be that most planets with life never evolve it and remain stuck with less efficient energy sources, limiting the complexity that can evolve. Or perhaps the filter is mass extinction events. Earth has experienced several major mass extinctions, events where the majority of species died. The most famous is the asteroid impact 66 million years ago that killed the dinosaurs and most other species alive at the time. These events are catastrophic, but they also create opportunities. The extinction of the dinosaurs allowed mammals to diversify and eventually gave rise to primates and humans. Without that extinction, intelligence might never have evolved on Earth. But mass extinctions are random. A planet might go billions of years without a major extinction event, allowing one dominant form of life to persist and preventing the turnover that drives evolutionary innovation. Or a planet might experience too many mass extinctions, preventing complex life from gaining a foothold. Earth might have been lucky to have just the right number and timing of mass extinctions to produce intelligence. Think about how many things had to go right for you to exist. Think about the chain of events stretching back billions of years. At any point, things could have gone differently, and you wouldn't be here. The same is true for our civilization. We're the product of countless contingencies, accidents, and unlikely events. Maybe that's normal. Maybe every civilization is equally improbable. Or maybe we really are special, a cosmic fluke. There's a concept in philosophy and physics called the anthropic principle. In its weak form, it simply states that we observe the universe to be compatible with our existence because if it weren't, we wouldn't be here to observe it. This seems trivial but has profound implications. For example, if the fundamental constants of physics were even slightly different, stars wouldn't form, or chemistry wouldn't work the same way, or the universe would have collapsed or dispersed before life could evolve. The fact that we exist means we're necessarily in a universe where these constants have the right values. Similarly, we're necessarily on a planet where all the filters up to this point have been passed. We couldn't be on a planet where life never started or intelligence never evolved, because then we wouldn't exist to wonder about it. This is sometimes called the observer selection effect. We're selected from the subset of all possible universes and planets where observers can exist. This doesn't tell us how common that subset is. We might be typical, one of countless observers in countless locations, or we might be extraordinarily rare, winning a cosmic lottery against unimaginable odds. The strong anthropic principle goes further, suggesting that the universe must have properties that allow life to develop because if it didn't, there would be no observers. And in some sense, the universe requires observers to exist. This gets into deep philosophical and even metaphysical territory and is more controversial. But it highlights the connection between our existence and the fundamental nature of reality. In the context of the Great Filter, the anthropic principle tells us that we should expect to find ourselves in a situation where all past filters have been passed, regardless of how unlikely those passages were. But it doesn't tell us anything about future filters. We might be typical of civilizations that made it this far, or we might be in an unusual situation. We don't have enough data to know. This is why finding evidence of other civilizations, or their absence, is so important. It would help us understand whether we're typical or exceptional, and that, in turn, would help us estimate the location and severity of the Great Filter. Let's imagine for a moment that we do survive the next few centuries. We stabilize our climate, we avoid nuclear war, we develop safe AI, we prevent catastrophic bioterrorism. We establish permanent settlements on the Moon and Mars. We build space habitats. We send generation ships or automated probes to other star systems. We become a true spacefaring civilization, with significant populations living beyond Earth. What then? If we reach that stage, we become part of the solution to the Fermi paradox rather than part of the mystery. We become the aliens that other civilizations might someday detect. We might encounter the ruins of civilizations that didn't make it through the filter, and we'd have a responsibility to study them, to learn from their failures, to preserve their memory. We might find planets with simple life, and we'd have to decide whether to protect them or terraform them for our own use. These would be profound ethical questions. We might also encounter other civilizations that did make it through. First contact would be the most significant event in human history. It would tell us we're not alone. It would give us peers, competitors, perhaps friends or enemies. The nature of that contact would depend on the circumstances. If we encounter another civilization at a similar level of development, spread across multiple star systems but not dominant in the galaxy, we might form alliances, trade knowledge, avoid conflict. If we encounter a far more advanced civilization, we'd be at their mercy, hoping they're benevolent. If we encounter a less advanced civilization, we'd have to decide what kind of elder species we want to be. But all of this is contingent on surviving the next few critical centuries. We're at a bottleneck, a vulnerable point in our development. We have powerful technologies, but not the wisdom or social structures to manage them safely. We're divided politically, culturally, and economically at a time when we need global cooperation. We're aware of existential risks, but not mobilizing resources to address them at the scale required. We're in the filter, and we don't know if we'll make it through. Let me paint a picture of what our current moment looks like from a cosmic perspective. Imagine an alien astronomer observing Earth from a planet hundreds of light years away. They'd see our past, light that left Earth centuries ago. If they're looking right now, they might see an industrializing world, smoke from factories, the beginnings of radio transmissions. They'd see a species on the cusp of technological transformation. If they keep watching over the next few centuries, what will they see? Will they see us spreading into our solar system, building orbital habitats, sending missions to other stars? Or will they see the radio signals stop, the lights go out, the planet go quiet? Will we be another data point in the cosmic graveyard, another civilization that almost made it? From our perspective, right now, in the early 21st century, we're at a pivotal moment. The decisions we make in the next few decades will shape the next few millennia, if we have a next few millennia. We're deciding whether to address climate change seriously or let it spiral out of control. We're deciding whether to regulate dangerous technologies or develop them recklessly. We're deciding whether to cooperate globally or fracture into competition and conflict. These decisions matter. They might matter more than any decisions humans have ever made. And most people don't realize this. Most people go about their daily lives, worried about paying bills and raising families and pursuing careers, unaware that we're living through what might be the most critical period in human history. There's a disconnect between the cosmic scale of what's at stake and the mundane concerns that dominate most people's attention. This is understandable. We evolved to respond to immediate threats and opportunities, not abstract existential risks that might materialize decades or centuries from now. But it's also dangerous because these abstract risks are real, and they require our attention and action. Some researchers have tried to quantify existential risk. Toby Ord, in his book, The Precipice, estimates that humanity faces about a 1 in 6 chance of extinction or civilizational collapse this century. 1 in 6. Those are Russian roulette odds. Would you play Russian roulette with 1 bullet in a 6-chamber revolver? Of course not. But that's the game we're playing with our civilization, whether we realize it or not. Ord's estimate is based on assessing various risks: nuclear war, climate change, pandemics, AI, and others. Other researchers have different numbers, some higher, some lower. But there's a growing consensus among those who study existential risk that we're in a dangerous period. This brings us back to the great filter with renewed urgency. We're not just interested in this as an abstract intellectual puzzle. We're interested because our lives depend on understanding it. If we can identify the filter, we can try to overcome it. If the filter is nuclear war, we work on disarmament and conflict resolution. If it's climate change, we work on decarbonization and adaptation. If it's AI, we work on safety and alignment. If it's multiple things, we work on all of them. But we're working against time and against our own nature. Humans are not good at long-term thinking. We discount future risks heavily. We're tribal, often putting the interests of our own group above humanity as a whole. We're susceptible to misinformation and ideology. We're sometimes irrational, emotional, short-sighted. These traits helped us survive in the ancestral environment, but they're liabilities when facing global, long-term, existential challenges. We need to be better than our instincts. We need to think on behalf of all humanity, present and future. We need to act with wisdom and foresight. Can we do it? History gives us reasons for both hope and despair. On the hopeful side, humans are also capable of amazing things. We've built civilizations, created art and science, landed on the moon, eradicated diseases, connected the world through technology. When we're at our best, we're cooperative, creative, compassionate, and brilliant. We've solved problems that seemed insurmountable. We've changed our behavior when presented with evidence and moral arguments. The hole in the ozone layer was a global environmental crisis caused by chlorofluorocarbons. The world came together, signed the Montreal Protocol, phased out the offending chemicals, and the ozone layer is recovering. It's proof that we can address global problems when we choose to. Maybe we can do it again for climate change, for biosecurity, for AI safety. On the despairing side, we've also waged countless wars, committed genocides, enslaved each other, degraded our environment, and created weapons capable of destroying ourselves. We often act tribally, selfishly, and short-sightedly. We've known about climate change for decades, and our response has been inadequate. We've known about the dangers of nuclear weapons for decades, and we still have thousands of them on hair-trigger alert. We develop powerful technologies without fully considering the risks. We might not be wise enough to save ourselves. Which side of our nature will win out? That's the question. And it's not just a question about humanity. It's a question about intelligence itself. Maybe intelligence, as a trait, is self-limiting. Maybe the same curiosity and tool-making that allows a species to develop technology also leads them to develop weapons and unsustainable practices that destroy them. Maybe the great filter is built into the nature of intelligence itself. If so, then every intelligent species faces the same test, and most fail. But maybe not. Maybe some make it through. Maybe we can be one of them. Let's talk about what we can do, practically, to improve our odds. First, we need to spread awareness of existential risks. Most people don't think about these issues because they're not aware of them or don't understand their severity. Education is crucial. We need to teach people about the great filter, about the risks we face, about the importance of long-term thinking. This isn't just for scientists and policymakers. It's for everyone because democracies depend on informed citizens, and addressing these challenges will require public support. Second, we need to fund research into existential risk reduction. The amount of money spent on studying and mitigating these risks is trivial compared to their importance. We spend more on entertainment and cosmetics than on ensuring our survival as a species. Organizations working on AI safety, biosecurity, nuclear de-escalation, and climate change deserve far more support than they currently receive. Governments, foundations, and individuals should prioritize this funding. Third, we need to develop better institutions for global cooperation. Many of our existential risks are global in nature and require coordinated responses. Climate change doesn't respect national borders. A pandemic can spread worldwide in days. AI developed in one country affects everyone. We need international bodies with the authority and resources to address these challenges. The United Nations is a start, but it's often hampered by political divisions and lack of enforcement mechanisms. We might need new institutions designed specifically for existential risk management. Fourth, we need to become a multi-planetary species as quickly as feasible. This doesn't solve the underlying risks. We can destroy ourselves on multiple planets just as easily as on one. But it does provide some redundancy. A catastrophe that wipes out life on Earth wouldn't necessarily affect a self-sustaining colony on Mars or in space habitats. Spreading beyond Earth is a form of existential insurance. It's also a powerful symbol of our ambitions and our refusal to accept limits. Fifth, we need to cultivate wisdom alongside knowledge. Technology gives us power, but power without wisdom is dangerous. We need educational systems that teach critical thinking, ethics, long-term thinking, and global citizenship. We need to value wisdom as much as we value innovation. We need leaders who think in terms of centuries and millennia, not just election cycles or quarterly earnings. These are not easy tasks. They require changes in how we think, how we organize society, how we allocate resources, and how we educate our children. But they're necessary if we want to survive and thrive. Now, let's circle back to the most chilling possibility. What if we're too late? What if we've already set in motion processes that will lead to our downfall? Climate feedback loops might already be irreversible. AI development might already be advancing too fast for safety research to keep up. Biological knowledge might already be widespread enough that preventing catastrophic bioweapons is impossible. Nuclear arsenals might be too entrenched in security doctrines to be dismantled. If this is the case, if we're already doomed, what should we do? One option is to fight anyway, to try to beat the odds even if they're against us. Another is to accept our fate and focus on making our remaining time meaningful. Another is to leave a legacy, to send messages or artifacts into space that might be found by others, telling them who we were and warning them of the dangers we faced. The Voyager spacecraft, launched in the 1970s, carried golden records with sounds and images representing life and culture on Earth. They're now in interstellar space, traveling outward, and will orbit the galaxy for billions of years. If we go extinct, these might be all that remains of us, a message in a bottle floating in the cosmic ocean. Is that enough? Is it enough to say we existed, we tried, we created beauty and knowledge, even if we couldn't survive? Or should we demand more of ourselves? I think we should demand more. We should refuse to accept extinction as inevitable. We should fight for our survival and the survival of all life from Earth. Not because we're guaranteed to succeed, but because the fight itself is meaningful. Because future generations, if they exist, will judge us by whether we rose to the challenge or surrendered to it. Let me share a perspective from Carl Sagan, one of the great advocates for space exploration and scientific thinking. He described Earth as a pale blue, a tiny speck in the vastness of space. He argued that this perspective should humble us, make us realize how precious and fragile our world is, how foolish our conflicts and divisions are in the face of the cosmos. He wrote about the responsibility of being, possibly, the consciousness through which the universe understands itself. If we're alone, if there's no one else out there, then we carry an enormous burden. We're the only eyes through which the universe sees itself, the only minds through which it thinks about itself. To destroy that, to allow that light to go out, would be a cosmic tragedy. Even if we're not alone, even if there are others, we're still unique. No other species has our history, our art, our perspective. No other species has Mozart's music or Shakespeare's plays or the scientific insights of Einstein and Darwin. No other species has your experiences, your thoughts, your potential. All of that would be lost if we fail. So what's the answer to the great filter? Where is it? Is it behind us or ahead of us? The honest answer is, we don't know. We have theories, speculations, models, but we don't have certainty. We're navigating in the dark, trying to avoid dangers we can only partially see. But that's okay. Uncertainty is not an excuse for inaction. We can still work to reduce the risks we can identify. We can still strive to be wise and careful. We can still reach for the stars. Maybe we'll find, in the coming decades or centuries, that the great filter was behind us all along. Maybe we'll discover microbial life on Mars or Europa, but no signs of intelligence elsewhere. Maybe we'll spread across the solar system and eventually to other stars, and we'll find that we're the first, the precursors, the elder race that others will one day look up to. That would be a profound responsibility, but also an incredible opportunity. We'd have the chance to shape the future of life in the galaxy, to fill empty worlds with descendants of Earth, to ensure that the universe is not silent but full of thought and life. Or maybe we'll find evidence of other civilizations that made it through the filter. Maybe we'll receive a message from the stars, a greeting from cosmic neighbors who survived their own dangerous transitions. That would transform everything, showing us that long-term survival is possible, that we're not alone, that the universe is richer than we dared hope. Or maybe we'll face the filter in our future and fail. Maybe our signals will stop, our lights will go out, and we'll become another cautionary tale, another civilization that almost made it. If that happens, we won't be around to know it, but the silence of the universe will deepen, one more voice added to the missing choir. Which future we get depends, in part, on us, on the choices we make, on whether we can overcome our divisions and short-sightedness, on whether we can develop wisdom to match our power. The Great Filter is a test, and we're taking it right now. We don't know if we'll pass, but we have to try. Ask yourself one final question. What will you do with this knowledge? Will you go back to your daily life unchanged, or will you let this shift your perspective? Will you think about the long-term future of humanity? Will you support efforts to reduce existential risks? Will you talk to others about these ideas? The Great Filter is not just an abstract concept for scientists and philosophers. It's about the survival of everyone you love, everyone who will ever live, all the potential futures that might or might not come to be. Look up at the night sky one more time. See those stars, those islands of light in the darkness. Each one might have planets. Some of those planets might have had life. Some of that life might have become intelligent. Some of those intelligences might have built civilizations. And yet, we hear nothing. The great silence presses down on us, heavy with implication. We're either alone, or we're surrounded by graves, or we're being watched by those who have learned to hide. None of these options is comforting, but all of them are possible. The universe has given us a mystery, a question written in the silence between the stars. Where is everyone? And embedded in that question is a warning. Be careful. The path ahead is dangerous. Many have walked it before you, and none have returned. Or perhaps it's a different message. You're special. You're rare. Don't waste this chance. Or maybe, welcome to the test. Show us what you're made of. We don't know which message is correct, or if any of them are. But we know this. We're here, now, at a critical juncture in our history and possibly in the history of life in the universe. We have power and knowledge that previous generations could only dream of, and with that power comes responsibility. We have to choose, actively choose, to survive, to be wise, to think beyond ourselves and our immediate needs. The Great Filter is out there, somewhere in the past or future or both. It has claimed countless civilizations, or it has prevented them from ever arising. But it hasn't claimed us yet. We're still here, still alive, still reaching for the stars. As long as that's true, we have hope. As long as we continue to strive, to learn, to grow, to reach outward and upward, we have a chance. The story of humanity is not yet finished. The final chapter has not been written. We get to decide, through our actions and choices, whether that chapter is a tragedy or a triumph. Whether we'll be remembered by someone or something in the far future as the species that made it through, that passed the test, that brought life from Earth to the galaxy. Or whether we'll be forgotten, another silent world among trillions, our story lost to time. The universe is watching, waiting to see what we do next. The Great Filter stands before us, ancient and implacable. And we, small and fragile but conscious and determined, must find a way through. Not because it's easy, not because success is guaranteed, but because the alternative, the extinction of everything we are and everything we might become, is unacceptable. So we continue, we explore, we learn, we build, we cooperate, we survive. We reach for the stars, knowing that the path is perilous but walking it anyway. Because that's what intelligence does. That's what consciousness does. It persists. It endures. It refuses to go quietly into the darkness. And maybe, just maybe, if we're wise enough and lucky enough and determined enough, we'll make it through. We'll beat the odds. We'll pass the filter. And someday, on a world far from here, under a different sun, our descendants will look up at their night sky and wonder if anyone else is out there. And they'll have us to thank for the opportunity to ask that question. The great filter is real. The silence is real. The danger is real. But so is our potential. So is our hope. So is our determination to survive and thrive and spread life and consciousness across the cosmos. The universe may be silent now, but it doesn't have to stay that way. We can fill it with voices, with thought, with life. We can be the answer to the Fermi paradox, the civilization that made it, the ones who proved that the filter can be passed. But only if we choose to. Only if we act. Only if we recognize the moment we're in and rise to meet it. The choice is ours. The future is unwritten. And the stars are waiting.